Okay, so let's look at to this problem 7.60, page 347, and again now we are given a case of coaxial cable but with slightly difference in terms of current directions. So we are given this structure. We have the inner conductor which has radius of A, and this one you have the current flowing in negative Z direction, so you can simply draw like a cross, right? Because coming in negative Z directions. And also we have for the outer conductor here from B to C, now we have a current flowing in positive Z direction. You can simply draw as a dot because flowing to the positive Z directions. So now we are going to prove that the ACL of Maxwell equation obey the region B and C, right? So we have to prove that the H field that appear in this region B and C actually obey the Maxwell equation number 3. So based on our last lecture, we know that the third Maxwell equation given as curl of H is equal to the J. So now we have to find this curl of H expressions and make sure they are same with the J term that we found later. So this is our task now. So let's look at the first one. I want to find the J first. The J is actually, guys, the volume current density that actually exists within the outer conductor regions. So now we know that the J here actually flowing in positive Z direction. So we can have here the J actually total current over total area. Now we have total current actually become to I positive, and then total current, total area equal to pi C squared minus B squared, and the current flowing in positive Z, so you can simply put here positive Z direction. So and has unit of ampere per meter squared. So that's the J gas that actually flowing in the outer conductor, right, as shown here. So now we are going to prove this J value must be equal to the expression of curl of H. So that's our concern now. So let's proceed in finding the H using the ACL again. So now we're assuming that the L, the length of the cable, is much longer than the radius of C, so we can simply use the ACL to find the H field within the coaxial cable. Right? So I want to find the H field within the outer conductor. So let's point any position as your point of interest. Let's say that's my point of interest. So let's draw again the Amperian loop that must obey two conditions: must pass through the point and must completely close. So let's draw together. So that is our Amperian loop within the outer conductor, right? In between B and C. See, anyway. So let's say this one, guys, has a radius of R from the origin. Alright? Okay, so based on ACL equation, we know that closed integral the H dot dl is equal to the I enclosed. So look at carefully, guys. For the I enclosed, for this particular loop, actually it covers two types of current. The first one comes from the inner conductor, and then the other one comes partially from the outer conductor. So now you can say that for I enclosed, actually negative I, which is come from the inner conductor, and then plus the I that partially come from the outer conductor, which we can use this equation. Since the volume, can use the J dot ds. Alright, that's the way how we find I enclosed from the volume current. Right, must perform in vector dot J and ds. Okay, so now We know, guys, the J here given as above there, so we can simply proceed this one. We're gonna have here H for the dl here. For the circumference of this loop, we're gonna have here 2 pi r, and then a -1 s here, and now plus. So let's put in the J expressions as obtained earlier. So now we have I z directions. Now here pi c squared minus b squared. Now we have to take a sample of area for the outer conductor surface. So now since the area actually come from here, sample area, which also must be in the same directions with the J. So again here you're gonna have here z directions. So the ds for the z direction for the cylindrical structure, we have here r dr d phi. So bear in mind, guys, at this case the z remain constant. So now let's proceed with the limit. We have here minus I, and take out all the constant outside of integral part. Now we have here I again positive. Now pi c squared minus b squared. Integration, now the r actually r dr, and the phi d phi. The phi, we know that actually a full circle, so we can just set 0 to 2 pi. Meanwhile, the r here, guys, actually the current enclosed within the loop, which from b until r only. Again, I repeat, so this r limit actually only consider the current enclosed within the loop, whereby the current flowing appear from r equal to b at this point until r equal to r at that point of interest positions. So here you must put b until r. Okay, so let's proceed again. We're gonna have here negative I plus, you can find finally here the I over pi c squared minus b squared. Now we have here r squared minus b squared over 2. Now we have 2 pi, so we can simply delete the 2 with this 2, the pi with the pi, and finally can have simplified versions with the I over times r squared minus b squared over c squared minus b squared minus 1. Okay, that's the right hand side equations, which is the current enclosed within this loop. So now I have to find the h. So just bring all these 2 pi r down there. So now we have here the I 2 pi r, then the whole term here r squared minus b squared over c squared minus b squared minus 1. So now we have in phi directions. Okay, so that's default directions when the I flowing in z. So by that we can have the h will flow in positive phi directions. So with unit of ampere per meter. Okay, guys, so now we have a h already. So now we need to put this h value in terms of curl operations. So let's look at to your table of curl. From textbook we can see that the curl of h for the case of cylindrical is given as here, the curl of h given as 1 over r d h z over d phi minus d h phi over dz, now in r directions, plus here we have dhr component over dz minus dhz component over dr, and now the whole term belongs to the phi directions. And then lastly down here, plus 1 over r d over dr. You have r h phi component minus dhr component over the phi, and the whole term belongs to the z directions. Okay guys, so we know that guys, from our h value we obtained earlier, the h obtained as, let me write down here, you can see, so the I over 2 pi r, and then the r squared minus b squared over c squared minus b squared minus 1 in phi directions. So sorry for that, this one actually our r. Alright, okay, so the r squared minus b squared. Alright, so let's look at to the h component. So from here you can see that the h only exists in phi component. So guys, the whole term here is actually our h phi component. So whereby we don't have any h r component, we don't have any h z component, so we can just ignore this term straight away. We also can ignore this term, also this term, also this term. So now left only two terms above here and down there. So let's look at the above here. Now even though we have a hash in phi term, in phi component, but in this expression guys, we don't have any z variable. So by right, we also will have 0 for this derived differentiations, right? So now we only left the left term down here. So let's put this h phi component inside these expressions. We're going to have here the curl of h. Finally, we're going to have 1 over r d over dr r. Now let's put all the term here within this. Now we have 1 over 2 pi r, so r squared minus b squared, c squared minus b squared minus 1, and now in z direction, right? Because obtained from here, so z must be there. So now let's simplify the equation. Now we can just cancel out the r term, isn't it? And then let's differentiate the whole term inside here with over r, and now take out all the constant value, which is I over r. You're gonna have 2 pi. So now differentiates the whole term of r squared, b squared, c squared minus b squared minus 1. Now we have in z directions. Okay guys, so we can see that from here, after we differentiate this term, we're gonna have here z I, which is 2 pi r. Now we're gonna have here 2r over c squared minus b squared. Now again we can simply delete the 2 here and with 2 up there, and also the r down here with the r up there, and finally gonna have here the curl of h which equal to the z directions I over 5 c squared minus b squared, which exactly same that we obtained earlier up there. Can you see? So now we have proved that the H in the third region or the outer region actually obey the ACL of Maxwell equation. Right? So it's a proof already. So guys, so I hope you can try yourself. So make sure you get familiarized with all these equations and also the curl expressions. So all the best and make sure you try. So thank you.